and welcome to another episode of Hollier's Help Homework for Feedback. Today we're looking at thermochemical calculations. Okay, so we're going to write a chemical equation for the dissolution of glucose. We're given that 11 kilojoules per mole is absorbed, and we need to determine the mass of glucose dissolved if 500 joules is absorbed in total. The first thing we need to think about is what the heck is dissolution of glucose. All it is meaning that glucose is dissolving in water to become aqueous glucose. So glucose solid to glucose aqueous. And of course we've got a delta H in there to make it the thermochemical equation. The delta H has got a positive value because it is absorbed, meaning it's an endothermic reaction. Now we know that we can calculate the delta H of solubility by dividing delta H, the amount of energy that's produced by a reaction, by the moles of the substance that has caused that energy change. We can rearrange that to make N the subject so that we're calculating the moles of glucose involved, and we substitute those numbers in. 500 joules is absorbed, so that's a delta H, and 11 kilojoules per mole is absorbed of glucose. And so we get 0.045 moles of glucose. Now note that I'm leaving a lot of extra significant figures because you do not round off before you get to the final answer. So we've got the number of moles, but the question asks for the mass of glucose. So we now have to go to our little favourite N is equal to M over MM calculation, and we can work out the molecular mass by adding up all of the appropriate atomic masses, and we can substitute that information in and come up with a mass of 8.188 grams of glucose. But of course, if you have a look at the original information, 11 kilojoules per mole means that we've only got two significant figures in our least significant figures number. And so we report it to two sig figs. 8.2 grams of glucose would be required to be dissolved to absorb 500 joules of energy into the water. Our next question is a little bit more complicated. We're neutralising sodium hydroxide with hydrochloric acid. We're measuring the temperature change, and we're calculating the heat released and then the enthalpy change for the reaction. Now, I think that what they're talking about is they want the delta H per mole. So we're first of all going to write down the equation, make sure that we've got the right states of matter, make sure that it's stoichiometrically correct, balanced, and we don't have to write the delta H because they haven't asked for a thermochemical equation. But we're going to calculate the heat released first, and the heat released has a symbol Q. We can get that equation from our data sheet. Q is equal to MC delta T. Now this is all about the thing that is being heated. It's the water that's being heated. So first of all, we must use the total mass of water. So it's 25 mils of one solution plus 50 mils of another solution to make a total of 75 mils of water, which weighs 75 grams. We're going to convert it to 0.075 kilograms because the specific heat capacity of water is given in joules per kilo per Kelvin, and you can get that from the data sheet as well. Now, given the temperatures, we get a change in temperature of 0.9 degrees C. There's no need to convert that to Kelvin because 1 degree change in Celsius is equivalent to 1 degree change in Kelvin, so we don't need to convert that. We get a total of 282.15 joules of energy has gone into heating up that solution, and we're going to just change it to kilojoules. So we've calculated the heat released into the water, and now we can turn that into the enthalpy change. Enthalpy change is delta H, whereas the heat of reaction is Q. So the delta H is just minus Q. Delta H has got a minus value because it has increased the temperature of the water. Increasing the temperature of the water means it's an exothermic reaction, and delta H should have a minus value. So we can now calculate the enthalpy of neutralisation using this equation. The delta H of neutralisation is equal to the delta H, the amount of energy that has been created from this reaction divided by the moles of the substance that has caused that change. Now we're going to be using the information from sodium hydroxide because we're told that hydrochloric acid is in excess, and therefore the amount of sodium hydroxide is what's going to limit the amount of neutralization that's going to occur. So we use N is equal to CV and we get 0.005 moles of sodium hydroxide. We substitute that in and we find that we have minus 56 kilojoules per mole, and we take that to two significant figures because we have got 0.20 moles of sodium hydroxide as being the least precise of the information that we are given. So Hollier's top tips for thermochemical equation calculations. When we're looking at Q, the heat of reaction, we're looking at, it's all about the water. How much mass of water is there? And that mass of water has to have the correct units. We've got to look at the specific heat capacity of water and figure out what units of mass are used in that. Joules per Kelvin per kilogram is what's written on the data sheet. So you have to have the mass of water in kilograms. Then once we've calculated Q, we don't really care about the water anymore. What we care about is the reactant. So we turn Q into delta H, and then you can use delta H to find the amount of energy per mole of reactant. So how many moles of the reactant? That's what you're really interested in here. And how many moles of that have caused a change in temperature of the water? That's what it's all about. So Q, it's all about the water. Delta H, it's all about the reactant. I hope you've enjoyed this.